Hello, everyone, and welcome to today's presentation. I'm excited to share with you some fascinating insights on how CO2 can be transformed into a variety of valuable products. Our focus will include not just chemicals and materials, but also the promising potential of methanol as a future fuel. We'll explore the processes involved, current challenges, and innovative research ideas, particularly those by Dr. Ahsan Ali on direct air CO2 capture and its applications in vehicles. So, let's get started and see how this important topic unfolds. So, while current technologies are promising, smart research initiatives have the potential to make this technology more affordable and compact. Imagine a future where vehicles can do more than just move. They could actually capture CO2 directly from the air. This CO2 could then be converted into methanol, which would serve as fuel for the vehicle itself. These types of vehicles are called direct air carbon dioxide vehicles, or DACVs for short. Now, this idea might sound like science fiction, but it's far from impossible. It's a challenge that requires innovative effort and creative thinking to turn into reality. To put it into perspective, think about how far technology has come. For example, IBM's first computer in 1956 was huge, big enough to fill an entire room, and it only had 5 megabytes of storage. Today, we carry smartphones that fit in our pockets, and they do way more than those old computers ever could. What's exciting is that we can expect a similar leap forward in clean fuel technologies. This progress will be driven by smart, innovative scientists and engineers who are dedicated to solving some of our biggest environmental challenges. So, the idea of DACVs isn't just a dream. It's a future that's within our reach if we continue pushing the boundaries of what's possible. Before the industrial era, the amount of carbon dioxide in our atmosphere was around 280 parts per million. That's a relatively stable level that Earth's climate managed to handle for thousands of years. But then, as we started burning fossil fuels, like coal, oil, and gas, the CO2 levels began to rise sharply. Today, we're over 420 ppm, which is the highest in at least 800,000 years. That's more than 140 ppm of extra CO2 added to our atmosphere in just a short time. This increase has had a significant impact. Our planet's average temperature has gone up by about 1.2 degrees C compared to pre-industrial times. That might not sound like a lot, but it's enough to cause serious changes in weather patterns, sea levels, and ecosystems. To address this, the Paris Agreement was established. Its goal is to keep global warming well below 2.0 degrees C and ideally limit it to 1.5 degrees C. This is crucial because the more we warm the planet, the greater the risk of dangerous and irreversible climate effects. So, understanding these changes in CO2 levels and temperature helps us see why urgent action is needed. It's about protecting our planet's future and ensuring a sustainable world for generations to come. To meet the overall climate goals, countries around the world need to act decisively. Specifically, we have to reduce global emissions by nearly half by the year 2030. That's a significant target, but it's essential if we want to stay on track. Ultimately, we aim to reach net zero emissions around 2050, meaning we balance the emissions we produce with those we remove or offset. Now, one of the most critical points is staying below a 1.5 degrees Celsius increase in global temperature. This isn't just a number, it's a threshold that helps us avoid the most devastating impacts of climate change. But here, the key, every fraction of a degree of warming matters. The closer we get to that limit, the greater the risks to people, ecosystems, and the entire planet. And that's why urgent and strong action is needed right now. We don't have the luxury of delay. The decisions and actions we take today will shape the climate of tomorrow, and our collective response is crucial to safeguarding our future. Let's take a look at some real-world examples of carbon recycling in action. In Iceland, Carbon Recycling International is leading the way by using CO2 to produce over 200,000 tons of sustainable methanol each year. This process not only reduces emissions, but also creates a valuable product that can be used in various industries. Moving over to Vietnam, Petro-Vietnam Fertilizer and Chemicals Corporation, or PVFCCO, is building a facility designed to capture 240 tons of CO2 daily. This captured CO2 will be used to produce environmentally friendly urea, which is essential for agriculture. Lastly, in Iran, Party's petrochemical company is working on developing a plant that aims to capture and utilize 800,000 tons of CO2 annually for similar purposes. These examples highlight how different regions are adopting carbon recycling technologies to reduce emissions and produce useful products, aligning perfectly with our overall theme of transforming carbon into a valuable resource. Let's start with the electrolysis of water to produce hydrogen. As you can see, the chemical equation shows that 2 molecules of water, or H2O, are split into 2 molecules of hydrogen gas, H2, and 1 molecule of oxygen, O2. This process is fundamental because it allows us to generate hydrogen, which is a clean fuel source when produced sustainably. Moving on, the slide also covers the thermal decomposition, or cracking, of carbon dioxide. The chemical equation here indicates that 6 molecules of CO2 break down into 6 molecules of carbon monoxide, CO, and 3 molecules of oxygen. This process is important in converting CO2, a greenhouse gas, into more useful chemicals. Finally, we see the reaction where carbon monoxide combines with hydrogen to produce methanol, CH3O. This reaction is quite significant because methanol can serve as a versatile fuel or chemical feedstock, connecting back to the overall theme of producing sustainable fuels and chemicals from various sources. Together, these reactions highlight different pathways to produce valuable chemicals and fuels, emphasizing the role of electrolysis and thermal decomposition in our transition towards cleaner energy options. Let's take a quick look at some key points from the literature on making methanol production more compact and efficient. One of the most promising advanced methods is plasma-assisted catalysis. This technique involves ionizing the reactants, which in this case are CO and H2, to boost their reactivity. The exciting part is that this can happen under milder conditions, meaning we can reduce both the size and energy requirements of the reactors. Another approach involves non-thermal plasma reactors paired with nanostructured catalysts. These combinations can significantly accelerate the reaction process and improve the overall yield of methanol, even when operating at lower temperatures and pressures. That's a big step forward in making the process more energy efficient and scalable. Finally, microreactors or structured monolithic reactors are also gaining attention. They offer high surface-to-volume ratios and excellent heat and mass transfer capabilities. This means we can miniaturize the entire process, making it suitable for modular deployment, what some are calling methanol-in-a-box systems. All of these innovations tie into the overall theme of our presentation, transforming methanol production into a more sustainable, flexible, and scalable process. Let's explore some exciting future directions in methanol synthesis. One key area is electrocatalysis and photo-assisted catalysis. These methods use renewable electricity or light to drive the chemical reactions, which means we could potentially produce methanol under ambient conditions. That's at normal room temperature and pressure, making the process more sustainable and energy efficient. Another important innovation is integrating reaction and separation steps into a single unit. This can be achieved with technologies like membrane reactors or reactive distillation. By combining these steps, we reduce complexity, improve efficiency, and lower costs. Additionally, incorporating real-time sensors coupled with AI-based control systems turns the process into a smart operation. This allows dynamic adjustments, optimizing performance and ensuring maximum efficiency at all times. When we combine these technologies, plasma activation, advanced catalysts, compact reactor designs, and process intensification, we open up a promising pathway. This integrated approach can drastically reduce the physical footprint of production plants and enhance their agility, enabling faster, more flexible responses to market demands. Overall, these innovations are aligning with the broader goal of making methanol synthesis more sustainable, efficient, and adaptable for the future. Hello, I am Dr. Asan Ali, a consultant specializing in renewable energy and climate resilience innovative solutions. I also have experience as a professor of biotechnology and bioenergy. If you're interested in connecting or discussing further, you can reach me at icenilator@gmail.com or call me at +9231355200950. For more insights and research ideas, please visit my website at dracenclimaton.com. I am based in Islamabad, Pakistan. Before we conclude, I encourage you to subscribe to the channel for more research ideas and updates. Thank you for your attention, and I look forward to engaging with you on these critical topics.